Consider a simple mechanical spring mass oscillator moving at a constant rate under the influence of a steady driving force. Physical systems of this type are modeled using a linear time invariant equation, expressed as P of d x equals f of t. This establishes that the system's behavior relies on the input signal. Under standard conditions, driving this system with a smooth 1 Hz sine wave yields a predictable result. Resonance occurs when the system's natural frequency is also tuned to exactly 1 Hz. However, the behavior changes when the input signal is swapped for a discontinuous 1 Hz square wave. If we now tune the system's natural frequency away from that 1 Hz input, pushing it up to 3 Hz, the expectations of the sine wave model no longer apply. The oscillator begins vibrating out of control, reaching a state of high amplitude excitation. This raises a fundamental question about the relationship between signal and response. We are driving the system at 1 Hz, yet it is reacting as if we are hitting its resonant peak at 3 Hz. The physical response indicates that the geometric shape of the input wave is a poor predictor of how the system will actually behave. Mathematically modeling this behavior requires an accurate description of the square wave, but standard calculus tools face significant hurdles. A Taylor series requires the error term, En of x, to approach 0, demanding an infinitely differentiable function. The square wave's jump discontinuities have undefined derivatives. The error terms blow up, making power series useless for periodic signals with sharp jumps. To model systems that survive these infinite bandwidth jumps, we must move beyond local approximations. The Fourier series offers an alternative by mapping periodic functions onto an infinite basis of sines and cosines. By using these integral formulas, we can determine the specific weighting of every frequency present within a signal, represented by the coefficients a sub 0, a sub n, and b sub n. When we apply these integrals to a standard square wave to find the b sub n coefficients, we must integrate the input signal against a sine wave across a full period. The integration boundaries produce a term involving cosine of n pi, which determines the final value of each coefficient based on the integer n. Because of the parity of the cosine function, when n is an even number, the terms cancel out to 0. This means even harmonics like 2, 4, and 6 Hz are mathematically absent from the signal. Only the odd harmonics remain, leaving a coefficient of 4 divided by pi times n. The resulting series demonstrates that a 1 Hz square wave contains a descending spectrum of odd-numbered harmonics. We can verify this weighting by looking at the partial sums of the series. S1 is the first term, the fundamental 1 Hz sine wave. Adding S2, which includes the 3 Hz harmonic, begins to flatten the peaks and steepen the vertical transitions of the wave. As we layer on S3, the 5th harmonic, these smooth trigonometric curves begin to approximate the discontinuous square shape. Each subsequent harmonic contributes less to the total shape, with their amplitudes decreasing by a factor of 1 over n. If we view this signal in the frequency domain, its composition becomes clear: a dominant bar at 1 Hz, followed by smaller bars at 3 Hz and 5 Hz. The sharp transitions of the square wave are actually the result of stacking an infinite series of smooth, continuous curves. We can now return to the mechanical equation, x double prime plus omega n squared x equals f of t, replacing the input f of t with this infinite Fourier series. The superposition principle dictates that a linear system processes every input frequency simultaneously and independently. Each frequency is modified by the complex gain formula, h of omega, which determines the system's amplitude and phase response. This gain formula is applied to every parallel harmonic track, from the 1 Hz fundamental to the infinite series of higher odd frequencies. The total physical response is the sum of these individual, isolated harmonic outputs. This allows us to re-examine the case where the system's natural frequency, omega n, is tuned to 3 Hz. The system's amplitude response is dictated by the denominator, omega n squared minus n squared, where n represents the frequency of the incoming harmonic. If we isolate the 3 Hz harmonic of the square wave, n becomes 3. As we sweep the natural frequency omega n toward 3 Hz, we are moving the system toward a specific mathematical condition. As omega n approaches 3, the value of the denominator approaches 0. This creates a resonant peak where the output amplitude spikes. The violent shaking occurs because the system is acting as a physical filter, amplifying the hidden 3 Hz component while largely ignoring the 1 Hz fundamental. While Fourier analysis provides a robust model for resonance, there is a persistent physical limit to this mathematical translation. If we zoom in on the vertical jump of the reconstructed square wave, a specific artifact appears at the corner. Even as we increase the number of terms in the series from 10 to 1000, the ripple remains. Adding more terms makes the ripple narrower, but it does not remove the overshoot at the corner. This persistent overshoot is known as the Gibbs phenomenon. The math dictates a permanent overshoot of roughly 8.9% of the gap, a constant that engineers must account for in any system processing sharp transitions. Understanding these harmonics allows us to synchronize complex mechanical systems, ensuring they respond predictably to signals that appear chaotic or discontinuous. Fourier analysis provides the translation layer required to understand how physical systems process the signals that drive them.